So again, in your groups, you're working on trying to get these simplified if you can. I say if you can. There's might be a little bit that you can't simplify. I hear people talking, which is good. Give you a little bit longer, and then we'll kind of run through some solutions and then just, remembrances of what we do when we simplify, what we can't do when we simplify. All of this, of course, everything is in preparation for the exam coming up on March 26th. It's not the week after spring break, it's the week after that. So when I say simplify, what words come to your mind as mathematicians? Common factors. Ooh, how did that move? There we go. So common factors is a good word two good words to think of when we're thinking about factoring. What do you mean when you say common factor? Like I think when I think of the word common factors, I have in my head it means something. What does it mean to you when you say common factors? Okay, so things that are alike. Things that are alike. Anything else that people think of or words that they think of when they see the word simplify? Reduce. Reducing is also part of simplifying, yes. Now, reduce is usually going to mean we have a fraction. In these cases, we don't. But yeah, that's a good word to have in there. Yeah. What else do we think of when we think about simplifying? Combining like terms is a phrase that I've used in class. Terms are things that are added and subtracted. Factors are things that are multiplied and divided. So when we're talking about these, the words have very important meanings, and so when we're going through that, that's why I'll specifically say things like combining like terms, not combining factors, because factors are things that multiply. So in the first one, do any of these things apply? They are like terms. Like terms means they are adding or subtracting the same thing. This is 2x's, that's 3x's for a grand total of 5x's. All right? What changes when we get to this next problem? Yep, the parentheses are the brackets. What do the brackets typically mean? Multiplication. So is there something that this first set of brackets is being multiplied by? 1. So we're gonna go ahead and do that first, leaving it just as negative 2x squared minus 5x plus 2y plus 8. So just getting rid of those brackets, recognizing that they're not actually serving a purpose for that first set, other than just to say, hey, I got all this stuff that's multiplied by 1. Is the second set of brackets being multiplied by something? Yeah, it's being multiplied by negative 1. And sometimes it's helpful to actually draw that 1 in there. So we see negative 1, so then you'll do, what's this property called? Distributive property. Okay. Like a distributor, someone who distributes something, they give 1 out to everybody. So that negative 1 goes on to each of those terms. So the 3x squared is now negative 3x squared. The x, which is a positive, is now a negative x. The negative 4x. Pause there for a second. Questions from anybody in here?
How do you
This one?
No, before that.
Here?
Yeah.
All right, so a root 7 and a root 7. So when we're multiplying two things together, so up here we said this is 2 x's. This here is 3 root 7s. So essentially, if I would have had root 7 plus root 7 plus root 7, that's 3 of them. All right. If I have this, that's like saying I have a negative root 7 minus a 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 root 7 for a total of 1, 2, 3, 4, 5, 6 of them. Well then, root 7 and a negative root 7 add to 0. Root 7 and a negative root 7 add to 0. Root 7 and a negative root 7 add to 0, leaving me with 1, 2, 3 that are all negative, so I have negative 3 root 7s. So that's like in long form, adding, subtracting what happened. In short form, it's saying I've got 3 root 7s here, I got negative 6 of them here. So a grand total of 3 minus 6, so negative 3 root 7s. So go ahead, see if you can figure out which ones are not true, which ones are true, and if they're not true, one counterexample is all you need. This is hard. This is hard. Yep. For the first one, did anybody come up with a counterexample? What do you get?
Square root of 4 plus the square root of 16 is not equal to the square root of 20.
Yeah, so the square root of 4 plus the square root of 16 is 2 plus 4, which is 6. The square root of 4 plus 16 is the square root of 20. And 6 does not equal the square root of 20. So there we go, I got a counterexample. If you use the same process, what would it be if we did the square root of 4 times the square root of 16? Well, that's going to be 2 times 4, which is 8. And if we take this and say, well, what's the square root of 4 times 16? What's 4 times 16? That would be the square root of 64, and that's 8. So that's good. Now, you can't go through and do all of them, right? But we've got one example to show that it does work. We could go and find another one, and we would actually find that whatever number we do put in, this one is true. So this one does fall under the category of true. This one we just proved was false. How do you tackle the next thing? What does that even mean? 4 to the 3 halves. Yeah, I'm going to go away from green. I don't like green. That's easier to see. What is 4 to the 3 halves? But what does 3 halves mean? 1.5 as a decimal. Yeah, but as a fractions, when you have exponents as fractions, that's a good way to point this out. When you have exponents that have fractions in them, you're going to usually and desirably, and I want you to, leave them as fractions. So the other day in class we said if we had something like this, square root of 2, that's the same as 2 to the 1/2 power. The third root of 2 is 2 to the 1/3 power. And then we remember other things like if I have a to the x raised to the y, that would be a to the x times y. When you have powers raised to powers, they multiply. The reason I do that is because here, I actually could rewrite this as 4 cubed times a half. Because 3 times a half is 3 halves. Which means this could have been written as 4 cubed to the 1/2. So what's going on is I'm, in essence, unsimplifying that exponent. Because at first, if you look and you go, I don't know 3 halves, or I don't know how to make my calculator do that, this is what's going on. So 3 halves is the same as 3 times 1/2. And if I'm multiplying exponents, that meant I had exponents raised to exponents. So 3, I could have also written this as 4 to the 1/2 raised to the 3. Those are the same thing. Because 3 times a half is the same as a half times 3. This would be 3 times a half. This is a half times 3. But either way, then you can do this, 4 cubed. Remember that from Tuesday? Was it Tuesday? The last time we met? 4 times 4 times 4? 64. And what does the 1/2 mean? Square root. Square root of 64 is 8. Check the other one out. What's this? So this inside here is 4 to the 1/2. What does the 1/2 mean? Square root of 4. What is the square root of 4? 2. So I'll have 2 cubed. 2 times 2 times 2, which is 8. Basically saying, does this simplify into this? What's going on over here? Simplifying a habit of either thinking this or writing it down to remind me to think it. Are there parentheses? Yes. Can these come together? No. Can these come together? No. They're not like terms, adding and subtracting. All right. Are there exponents? Nope. Are there roots? Yes. Can I simplify the square root of 2? No. 2 is prime. Can't be simplified. Is there multiplying? Yes, those 2 parenthesis sets are being multiplied. And either you think of a process that we've defined in the past, or, I'm just going to move that up out of the way for a second. Some of you have done it like this in the past, which works too. Think of an area method. So up here, I'm going to have root 2x, and this is plus 5. And this is root 2x, and this is minus 5. Because multiplying is finding area, like a rectangle. And I've got 2 parts of the first type. I've got 2 parts of the second type. So then, let's pick this one. That's the easy one to go with first. It's going to be negative 5 times 5, negative 25. All right. And then root 2x, we're going to do this box here. So that's going to be root 2x times 5. 5 times root 2x. The 5 is not under a square root, so it can't go into the square root. You cannot do 5 times 2. That root 2 is trapped. It's in its own jail cell. Can't go anywhere, cannot interact with other people. It stays in there all by its lonesome. This one here, negative 5 times root 2x. negative 5 root 2x. And then we have these two. They are both under the square root, which means they can interact with each other. So it's going to be root. What's underneath the square root? 2x times 2x. So the 2 times 2 is 4. And the x times x is x squared.
That's kind of like a Punnett square, right?
Kind of like a Punnett square, yep. Yep. So then, once you get all done, we're going to add them all together. Root 4x squared plus 5 root 2x. That's a negative, so it'll be minus 5 root 2x, and then minus 25. Combining like terms, this is a 5 root 2x, this is a negative 5 root 2x. They add up to 0. So now I've got this. And then I go back to my simplifying process. Are there parentheses? No. Are there exponents? Not like things being raised to exponents. There is an exponent on that x, but nothing I can simplify. Are there roots? Yes. Can I simplify this?
Wouldn't that be just 2x?
I'm going to do it like this first. The answer is yes, you are right. It's 2x. But how did we get there? We're going to split that up into the root 4 times root x squared. Because again, we can combine if they're both under the square root, which means we can separate them out into multiplying if they're under the square root. And I know the square root of 4, it is 2. The square root of x squared is x, because square root and squared are inverse operations. Final answer, 2x, those middle added to there, minus 25. And what was I asked? Let's select everything. Why is everything not selecting? Hold on. There we go. Move it all down. Are those equal? Yes. So again, showing that process. Now you could have done FOIL. FOIL is the same idea. For doing this here. I did it using the area method. Either one works. They are the same idea. All right, so now we go to here. Are these the same? So we start over here. What does squared mean? Squared means everything gets multiplied by itself. So I'm going to have this root x minus 1 plus 5 times root x minus 1 plus 5. Now we'll do it as FOIL. Root x minus 1 times root x minus 1 is root x minus 1 squared, because it's times itself. That's firsts. Outside, root x minus 1 times 5 will be plus 5 root x minus 1. Insides, because they're both in the inside of the big set, 5 times root x minus 1 will be 5 times root x minus 1. And then lasts 5 times 5. $25. root x minus 1, square root squared. Square root squared are inverse. This term here becomes x minus 1. These are like terms because they have the exact same root after it. Root x minus 1. I've got 5, got another 5, for a grand total of 10 root x minus 1s. So those actually combine into that one term. And then plus 25. And I can already see that this is not what's happening here. Because my final answer has to have a root x minus 1 in it somewhere. So if I was to look at this and say, where did they make the mistake? Here is a very common mistake that I see. That's why I did it on this one. People will sometimes see this squared and say, oh, I'll just square the 5, which is 25, and I'll square the square root, which would then just be x minus 1. And that is, again, 100% wrong mathematics. When there's two terms adding, so there's this term plus this term, that square can't come into each of them. Exponents move into each factor, but not into each term. So next up, rationalizing a denominator. So a little bit of new content here for this course. You may be seeing this in the past. The analogy I always say is, can you eat spaghetti with your hands? Technically, yes. Is it the right way to do it? Only because our culture says, no, you don't do it that way. It's messy. In mathematics, this is mathematically okay to write. It's messy, though. And again, going back to the they, whoever they were, who've defined how we all do it now. If I want this to be a more pleasant looking fraction, I have to not have a square root in the denominator. So again, the theys that define this said we do not do square roots in the denominator. So we do something called rationalizing the denominator. And some of you might wonder, why do we call it rationalizing? Well, because the square root of 2 is what's called an irrational number. And so we need to make it a rational number. And what we do when we rationalize is we, come on there, pen, multiply by 1. If you multiply something by 1, it's the same thing. So we look to this first one and say, all right, I'm going to multiply this by 1, but these all end up being fancy ones. What can I multiply the square root of 2 by to get rid of the square root? If I multiply the square root of 2 times the square root of 2, that would be the square root of 4. And the square root of 4 is 2. And then in the numerator, I've got square root of 3 times the square root of 2, which is the square root of 6. Again, when you're multiplying, if they're both under the same root, I can multiply them underneath that root. Next one down gets a little harder because now it's a cube root. So in order to get rid of a cube root, I have to have something cubed. So what that looks like would be this. So again, I'm going to multiply it by 1. But it's going to be the cube root of 9y squared times the cube root of, I shouldn't have put my parentheses there, 9y squared. Cube root of 9y squared times the cube root of 9y squared. So this is 1. Same thing in the numerator, same thing in the denominator. But the reason why I have to have 2 of them here is because to get rid of the cube root, I need to have 3 of them. When I do that, my denominator simplifies very quickly into 9y squared. My numerator will be the cube root of, and then since they're all cube roots, I can multiply underneath. 9 times 9 is 81. 81 times 2, 162. I have an x squared, and that's it for that, so I'll have an x squared. And I have y squared and y squared, so that will be y to the fourth. And that would be rationalizing the denominator. You can simplify at least one thing in the numerator. How do I know? Y to the fourth cube root. So again, if I just break just that one piece out, that could be rewritten as the cube root of y cubed times the cube root of y. Y to the fourth is the same as y cubed times y, so I split it up into two separate ones. This would then be y times the cube root of y. So here I would have y times the cube root of 162x squared y all over 9y squared. Well, look at that. This y reduces with that one. So then I have the cube root of 162x squared y. Make sure that root goes all the way over all of them. Over 9y. And then the last step to see if you could simplify even more would be to think, is there a number that goes into 162 that I know the cube root of? We did this the other day in classes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. And since that's over halfway, or getting up towards halfway there, that's as far as you would have to go. But then it would go to your calculators. Does 8 go into 162? Not evenly. Does 27 go into 162? People are checking their calculators quick. What?
27 to 162?
Yeah, 162 divided by 27? 6 times. Which means, we'll move that up there for a second. I'm just going to pull that one apart for all by itself. Cube root of 162. Cube root of 27. You said that would be the cube root of 6? Because 6 times 27 is 162. I chose this because I know the cube root of 27 is 3. So this will then equal 3 times the cube root of 6x squared y over 9y. Oh, look at that. I can reduce some more. Cube root of 6x squared y over y. And at that point, we are finished. How do I know? 6, there's no number that goes into 6 that we know the cube root of. X squared, that exponent is less than 3, so it cannot be simplified out. The y exponent is 1. We already actually did that in the step up there. And this y cannot interact with that y because that y is trapped in the cube root. This one is not. So again, the conjugate is if this was minus, this will be plus, so that when we FOIL it out down here, that middle term adds to 0, and that middle term will have the square roots in it, leaving me just the 3 minus 4 for a -1 denominator. Numerator, 5 times each of those, distributive property. -5 root 3 minus 10. And those cannot be combined because one of them is a root and the other one is just a number. So we're going to go through a few of these quickly. Let me cover them, and then I'll give you a pause. If you want to jot something down quick, you can do that. But in this first case here, we're going to multiply this by 1, which is going to be root 7 over root 7. That'll give me a denominator of 7. And then the numerator, I'll have root 28x. And then I'm going to take that root 28 over here, and I'm going to think, okay, 4 goes into 28. And I know the square root of 4 is 2. 7 is prime. So my numerator simplifies into 2 root 7x over 7. All right? And the x has a single power. So if this were x squared, sure, then I could do something, but it's not. And the 2 and the 7 don't reduce, so this would be the fully simplified version of this fraction here. Similar concept, but this time that x is not under the square root. So then this will be over 7. Again, I'm choosing root 7 over root 7, multiplying by 1, because that will be either you say root 49, which is 7. And then here, I'll have x times the square root of 28, because that x is not inside the square root. I just did square root of 28 over here, so I can replicate that here. So it would be 2x root 7 over 7. And do not, I mean, sometimes in a haste during an exam, people think, oh, I can reduce that. No, you can't. Roots only interact with roots, and the same roots. Those cannot interact. Here, I'm going to use the conjugate. Root 2x minus 1. Root 2x minus 1. Same exact thing, numerator and denominator. So denominator, first, outsides, so it's -1 times the root. Insides, positive root 2x. And then the lasts, 1 times -1 is -1. This and this add to 0, leaving me with 2x minus 1. The numerator, firsts, 2x root 2x, outsides, minus 2x, insides, minus root 2x, lasts, plus 1. And that will simplify into, let's see, I've got a root 2x and I got a root 2x, but this is 2x root 2x. That's just a root 2x. They cannot combine. While they do have the same root 2x, this has another variable. So these cannot combine. This is just a 2x. There's nothing else with just an x. And this is a 1. Actually, my numerator is simplified. Two x minus 1 in the denominator. And then I wonder, and people say, well, is there anything I can do here to reduce? And the answer is, if this identical item is identical to something entirely up here inside parentheses, I could, but there's not. These are all being added and subtracted, not multiplied. So I cannot reduce that. So that actually is done. And some of you might think, wasn't this actually a better looking thing? Yeah, yes, except the theys who decided this a long time ago says you can't have roots in the denominator. So that's what we did. So when solving when the variable is under the radical. So this is where we're headed to next. Here's our procedures of what we're going through. I'm going to give it to you at first, so we're going to do some problems and examples so you see how it works. First thing we're going to do is we're going to isolate the square root on one side and everything else to the other side. Then we're going to square both sides. The reason why we do that is that will eliminate the square root. All right, and I say be careful if it creates a quadratic, right? So sometimes you might square, we might have to do some foiling. These could be some bigger problems. Once I do that, hopefully then I have all my variables and there's no more square roots, and then I can just solve it like I've done before. If x is to the power of 1, then we move all the variables to one side of the equation, numbers to the other, and we solve for x. If x is squared, then we set the equation equal to 0, factor it. If x is a higher power than 2, that's when we did like factor by grouping. So these are like our generalized procedures that we're going to go through as we solve some of these. So that first one there is, so the first step was move all my square roots to one side. Are they? Yes. So then my next step is square this side, square that side. The squaring of a square root means I'm left with x, and then over here, 49. Yep. So I'm going to start with some easier ones and then move to more complicated. Next one down. Is my square root all by itself on one side? Yes. Because it's all by itself, I'm going to square both sides. Squaring a square root, those are inverse operations, leaves me on the left with x minus 4. On the right leaves me with 9. Well, now it looks like the algebra that we've done forever and ever. Got to move all my variables to one side, my numbers to the other, right? So add 4 to both sides of an equation. X equals 13. Next one down, all my exponents, not all my exponents, all my square roots are on the left. So I'm going to square both sides. Squaring a square root on the left leaves me with x minus 4. On the right, 3x, the whole thing squared, is 9x squared. Oh, now I've got a quadratic. Process with quadratics is set it equal to 0. So in order to do that, I'm going to add 4 and subtract x from that side. I'm going to add 4 and subtract x from that side, leaving me with 9x squared minus x plus 4. A times c is 36. 9 times 4 is 36. I need two numbers that multiply to positive 4 and add to negative 1. There aren't any. How do I know that? In order to add to a negative, that means they both have to be negative. Right? Negative 9 times negative 4 would be negative 36, or positive 36, but they're going to add to negative 12. There's not going to be a single pair that adds to negative 1. Well, then that means we're going to use the quadratic formula. This is A, that's B, that is C. Negative B is going to be positive 1, because here it was negative 1, so negative negative is positive. Plus or minus the square root of B squared, which is 1, minus 4 times A times C, all over 2 times 9. Inside here, 4 times 9 times 4, 16 times 9, like 166 or something, I'm not sure. Trying to do that one in my head. I'm not great at doing that in my head. 16 times 9, so it's going to be a 4 and 5 and 144. There we go. But it's going to be 1 minus 144, So under the square root, I'm going to have the square root of negative 143. 1 minus 144. I cannot take the square root of a negative number, so there are no real solutions. So while this might be set up as an equation, there will be no real solutions, no two places where an x goes in here that makes this thing true. Next one. Is my radical all onto one side? Yes. So I'm going to square both sides. On the left, I have x minus 4. On the right, so I'm thinking over here, squaring is the same thing as saying multiplying by itself. So I rewrite it like that, and then I'm going to FOIL x squared minus 4x plus 4. So I did it and simplified it there in my head. You're welcome to go back and verify my work. I have a quadratic. I need to set it equal to 0, which means I need to move the stuff on the left to the right. The reason why I do that is I want my x squared to be positive. So if I subtract an x from both sides, I get negative 5x. If I add 4 to both sides, I'll get 8. And now I'm thinking, are there two numbers when I'm working in my parentheses, or in my, sorry, I'm like mumbling. Because this coefficient is 1, I don't have to do the a times c. I don't have to do factor by grouping. I can just say, can this factor into two things? Two numbers that multiply to positive 8 that add to negative 5. Let's see, negative 4 and negative 2, they add to negative 6. There aren't any. So it'd be going back to the quadratic formula again, which I'm not going to do another step in here for that. But this is, again, going through the procedures of what we'd have to do. Square both sides. Not 4x. Ooh, I'm making my own mistakes. 2x, right? The roots and the radicals. So the inverse of square rooting is squaring. They eliminate one another. They're inverse operations. I have 2x equals 9. X equals 9 halves. But here's what happens. If you put 9 halves in here and take the square root, can you get negative 3? No, it's kind of like a tricky question. You can get an answer to this one, but you can never take a square root of something and get a negative value. You're like, oh, 81, square root of 81 is 9, not negative 9. It'll never be negative 9. Because you can't get a square root anyways. And then this one. Do I have all of my roots on one side? Yes. But here's where it gets a little more challenging. What we actually have to do first is move this over there. We have to eliminate one root at a time. Because now what I'm going to do is I'm going to square both sides. On the left, I'll have 2x plus 5. On the right, I'm thinking square means the same thing as multiplying by itself. FOIL, 9 minus 2 root 2x, not 2. Hold on. Minus, outside, sorry, 3 root 2x inside, minus 3 root 2x. And then lasts is negative times a negative, so it'll be positive. 2x. 2x plus 5 equals 9 minus 6 root 2x. Right, negative 3 and negative 3. And then plus 2x. So when you have two sets of square roots, you just have to eliminate one of them first. So we're going to square both sides. And then we have to go and do the whole process again. All right, here's my root. I'm going to leave that on this side. I'm going to move everything else to the other side. So I'm going to subtract 9 from both sides. I'm going to subtract 2x from both sides. On the left side, I have negative 4. On the right side, I have negative 6 root 2x. And divide both sides by negative 6. This will be 2/3 equals the square root of 2x. Square both sides. 4/9 equals 2x. Divide by 2, which is the same as multiplying by a half. 4/18 equals x. And then this reduces to 2/9. Ta-da! Lots of work going on there. Just going to look through these and find some common mistakes. So if this were a problem that you were doing for an exam, this goes to this step, goes to this step, goes to this step, goes to this step, goes to this step. From here to here, were there any mistakes made going from this step to that step? So, all right, we got the square root all on the left. We're going to square both sides, so we squared both sides. Is there a mistake? Should be 4. Or they should have done this and squared the whole thing. So when you're squaring, you square the whole side. Take 2x and square it. But they didn't. And by they means I didn't. So that should have been a 4. Okay. But ignore that for a second. We'll just go, what happened from here to here? Is this the same as that, like, is there a mistake happening from this step to this step? So take a look. Don't answer out loud. You're thinking in your head. You're looking at the steps. Is this step the correct logical next thing from what they did up here? All right? Is there a mistake from here to here? So that's what you're thinking. Thinking, looking. What do you think, Marcos?
No.
It's wrong? Yeah. Tell me what the mistake is. It's one of those two. It's right or it's wrong.
Doesn't the exponent cancel out the square root?
The exponent cancels out the square root, which is correct, leaving me just what's inside. So here to here, there are no mistakes. So yes, there was a mistake up here, but we're going to pretend. So this is what it's like to grade papers, to be a teacher. Oh, they made a mistake, and then I have to walk through all of your wrong work to see if you made more mistakes in the next step process, or if you just made that one mistake at the beginning, which honestly, if this were the only mistake you made, but you solved the rest of it the right way, you'd probably get almost full credit for me. Because you understand, like, hey, I'm doing all the right steps, but you forgot to square the two. Which to me is like, okay, you're going to get a weird answer, but it's not terrible. It's not like you're doing something mathematically like so egregiously wrong. All right. So from here to here, there's no mistakes. All right. Now, here to here, are there any mistakes? So it's just thinking, looking. If you have to write something down to verify for yourself, you're checking that. But you're looking to see, are there any mistakes? From, again, for going from this step to this step. Tommy, what do you think?
What was the question? Sorry, I was spacing out.
Are there any mistakes going from this step to this step? So here to, oh, let me go like this. Here to here, we said
Oh, no.
no mistakes.
I don't think
Here to here, what did they do?
they just brought it to the other side.
What did they bring to the other side? So if they had to show what's going on in between there, what would they have to have shown?
They would have to subtract the -2 on the right side
Subtracting 2x squared.
and bring it to the other side to the 4x squared.
Okay, so subtract 2x squared from both sides. What else did they do?
They got the variable by itself by using canceling out -32 to the other side.
And then subtract 32 from both sides. So here's my equal sign. -2x squared minus 32, -2x squared minus 32. They're the same thing. So if I do it from both sides, this adds to 0, this adds to 2x squared, this adds to 0, this adds to -32. So are there any mistakes? No mistakes. Thinking, looking, ready for me to call on you. This is where some of you are like, I always get called on because, or I only get called on when I don't know what's going on. I only get called on, or I never get called on when I actually know. Isn't that like in the head of most students? Yeah. Cameron, what do you think? Mistakes or no mistakes?
No mistakes.
Tell me what they did then to get from this step to this step. Divide by 2. Both sides. (32/16) is, or sorry, 32 over 2 is 16. Negative 32 over 16 should be -16. So should have been a negative. So they were missing a negative sign. Are there mistakes from here to here? You're looking,
No,
you're thinking,
because the square root.
I'm waiting for people to think. Yeah, that's all right. So Tommy, what would you like to tell us?
I'll say no because you're gonna have to square root 16 and the square root of 16 as well.
Right. So when you square root something squared, that's the plus or minus.
Oh, you have to put that?
Yeah.
Okay.
Yeah. If you square root something squared, so if your variable is an x squared and you take the square root of it, have to write the plus or minus because 4 squared is 16, -4 squared, also 16. All right, so then same idea. We go from here to here. Procedurally, what you should do is square both sides. You can see right away, lots of mistakes. They didn't square that side. And then this square somehow came in. Oh, no, I see what the mistake that they made here is they did, the square root of 4x squared is 2x, and then they had the square root of 32. So they tried to split this up, which you cannot do. You can split up the square roots when you're multiplying, but not when you're adding. Here to here, 2x. And then they subtracted 2x from both sides. So this step to this step is correct. And then they got no solution, which is a wrong answer. We're going to ignore that one. Come on, here we go. And then last problem here before we're heading out. In a case like this where it says, hey, solve for x. This requires you to remember the Pythagorean theorem. Anybody remember the Pythagorean theorem? Here, I'll let you just shout it out.
A squared plus B squared equals C
A squared plus B squared equals C
squared.
squared. And do you remember which side is A, which side is B, and which side is C? The hypotenuse is what? C. And in this case, which one is the hypotenuse?
74.
74. The side opposite the 90-degree angle, also known as the longest side. And then the other two, it doesn't really matter. One of them's A, the other one's B. So you go through the process. All right, A squared. 2x minus 1 squared plus B squared, square root of 49 squared, equals C squared, square root of 74 squared. Squaring means multiplying it by itself. And then here, square root of 49 squared,
49.
49. Because the square root and the square are inverse operations. You could have said square root of 49 is 7, and then square it to get me to 49. Square root of 74 squared is 74. On the left, firsts, outside, inside, lasts, plus 49 equals 74. 4x squared minus 4x plus 50 equals 74. This is a quadratic. Set it equal to 0, which means I need to subtract 74 from both sides. 4x squared minus 4x minus 24. 50 minus 74 is negative 24. Equals 0. Procedures for solving quadratics. Number 1, is there a greatest common factor? Yes. X squared minus 4x minus 6 equals 0. Oh, and now it's a coefficient is 1, so I'm thinking, are there two numbers that multiply to negative 6 that add to negative 4?
3 times 1. Oh, shit. 3 times, I don't know.
Where?
If you take out the 4, why is it still?
Oh, that 4 should be a negative x.
Oh, yeah, that was.
There we go. Because I divided a 4 out. So now it needs to multiply to negative 6 and add to negative 1. Negative 3 and positive 2. So my two answers would be x equals 3 and x equals negative 2. But only this one works because if you put in negative 2, you're going to get a negative side length. Don't forget, that's what you're working on. We'll see you after spring break. Lots to do over spring break. Lots of math.
Here, there.